For our last section in this chapter, we are going to be applying some counting principles to probability. Particularly, we'll go over some basic concepts of probability, and then we'll also go into binomial probability today. So we'll start off by talking about some basic probability. So when we calculate probability, generally we say success, quote unquote success, means that the desired outcome happens, whereas quote unquote failure means that the desired outcome does not happen. Okay, so if you were trying to find the probability of some event occurring, in the numerator, you'll want to put the number of ways in order to get the desired outcome and put it over the number of total possible outcomes. Now, when we talk about probability, we remember that probability is always going to be a value between 0 and 1. If it's equal to 0, that means it's an impossible event. And if it's equal to 1, that means it is a certain event. Now, you can write probabilities in the form of a percent. That's absolutely fine. Just remember, percent means over 100, which means it is going to be still between 0 and 1. All right, let's take a look at an example, a basic example. So 2 6-sided dice are tossed. Well, what is the probability that the total of the 2 dice is 7? Okay, so if we have 2 6-sided dice, we need to figure out what all the different possible outcomes are. And of those possible outcomes, how many ways are there for us to get a total of 7? Right? There are different ways you can get a sum of 7. So I'm going to go ahead and write out what all the possibilities are. So here's my first dice, my first die. And here's my second one. And I'm writing it this way so that I can add the two together and come up with a whole table of possibilities. So if I add 1 and 1, that gives me 2, 2 and 1, that gives me 3, and so on and so forth. So we can come up with all the different ways that we could get a specific sum. So if the first dice gives us a 1, 2, 3, 4, 5, and 6, and then if the second one gives us 1, 2, 3, 4, 5, or 6, then we can find out, well, how many different ways are there of getting, in this example, 7. So to get the probability of the event being getting a sum of 7 or a total of 7, we need to put down the number of ways to get 7, which in this case it looks like there are 6 different ways to roll a 7, and then put it over the number of possible outcomes. So starting with that 2 that we first wrote down, after we wrote down 1 through 6 and 1 through 6 on the top and on the left, all the way to when we got to 12. So how many different possible outcomes are there? It looks like it's 6 by 6, so there are 36 possible outcomes. So there are 6 ways to get 7, and there are 36 possible outcomes, so this is equal to 1 out of 6. You can absolutely change that into a decimal or into a percent if you'd like, but a fraction is just as good. 1 out of 6. All right, let's take a look at the next example. In a state lottery, a player chooses 6 different numbers from 1 to 40. If these 6 different numbers match the 6 numbers drawn by the lottery commission, the player wins the prize. What is the probability of winning? Okay, so a couple of things to note. It says that the player chooses 6 different numbers from 1 to 40. Okay, so this is without replacement. Now, before we can figure out the probability of winning, we need to know, well, how many different ways can you pick 6 numbers? Another thing to note is that it doesn't say that these 6 numbers have to be in a certain order, it just has to match. The 6 different numbers that you pick have to match the 6 numbers that are drawn. It doesn't say that they have to be written in the same order as they are drawn. Nothing like that. So order doesn't matter, so we're dealing with a combination here. So there are 40 numbers from 1 to 40, and you need to choose 6 of them, the 6 correct ones. But we need to figure out how many ways are there of choosing 6 numbers out of 40, because those are the total possible outcomes. Okay, so the probability of winning is there's only one way to win. You have to pick those exact 6 numbers, and you have to put it over the total ways to pick 6 numbers. So 40 choose 6 is going to give us the total number of ways to pick those 6 numbers. So that's going to be 40 times 39 times 38 all the way down to 34 factorial. And on the bottom we have 34 factorial times 6 factorial, so the 34 factorials cancel. That leaves us with 3,838,380. Okay, so in order to figure out the probability of winning, that means there is one way of picking those 6 numbers. And how many ways are there to pick those 6 numbers? 3,838,380. So what are your chances of winning? 1 in 3.8 million. Okay, let's talk about some big concepts when it comes to talking about probability of multiple events. So when you're dealing with more than one event, before doing calculations, you should think about what types of events you have. So for example, you could have independent events. This is where the outcome or the occurrence of one event does not affect the outcome or occurrence of the second. Okay, so no matter what you get for that first event, no matter what happens in the first event, it doesn't affect what happens in the second event. Those are what we call independent events. Then there are also what we call dependent events, which you can guess. This is when the outcome or occurrence of one event does indeed affect the outcome or occurrence of the second event. And then lastly, we have what we call mutually exclusive events. These are events that cannot both occur. Just like with the fundamental counting principle, when we're talking about multiple events happening and you're finding the probability, you still want to use that principle, that and means you're going to multiply, and or means you're going to add. So what's the probability that event A and event B happens? Well, you're going to multiply to find that probability. Okay, so we'll write this down. So if A and B are events from the same sample space, then the probability of A and B is equal to the probability of A times the probability of B when A and B are independent. Now, if it's asking about the probability of A or B occurring, then you're going to go ahead and add the probability of A plus the probability of B when those two events are what we call mutually exclusive, right? So A occurring and B occurring, those are two mutually exclusive events. So there's no way in which both A and B both occur at the same time. Now, if they're not mutually exclusive, then you're going to have to subtract out the part that gets overcounted. So normally you do probability of A plus probability of B, but now you have to subtract out the probability of A and B. So if they're not mutually exclusive, that means there's something that overlaps. Anything that overlaps when you add probability of A plus the probability of B, anything that overlaps is now counted twice. So in order to avoid counting something twice, you're going to have to subtract out the probability of A and B, and that way that will give you the proper probability of A or B occurring when A and B are not mutually exclusive. Okay, so let's take a look at example 3. A survey of college students found 56% live in a campus residence hall, 62% participate in a campus meal program, and 42% do both. What is the probability that a randomly selected student either lives or eats on campus? Okay, so first note that these are not going to be mutually exclusive. Why not? Well, first, there are 56% that live in a campus residence hall, 62% participate in a campus meal program. Even if you were to add those two, you can already tell that's more than 100%. So obviously there is some overlap. And in fact, it tells you that 42% do both. Okay, so the probability that a randomly selected student lives or eats on campus is going to be the probability that the student you've selected lives on campus plus the probability that that student eats on campus. And then you have to subtract out the probability that that student does both, lives and eats on campus. Now, we can use this because, well, first of all, it's asking you about whether a randomly selected student lives or eats. So, or, being the operative word, means you're going to add. But because they're not mutually exclusive events, we have to subtract out the students that do both. Now, in this case, probability that a student lives on campus is 56%. Probability that a student that you pick randomly eats on campus or participates in a campus meal program is 62%. And then you're told that 42% do both. So we have to subtract out those that are under both. Okay, so now it's just a matter of simplifying that, and that comes out to be 76%. So the probability that if you randomly select a student, that student lives or eats on campus is going to be 76%. Okay, let's look at the next example. You just bought a small bag of Skittles. Not that you could know this, but inside there are 20 candies, 7 green, 5 orange, 4 red, 3 yellow, and 1 purple. You tear open a corner of the package and begin eating. What is the probability that the first Skittle you eat is red, yellow, or purple? Okay, so the probability here is that we're looking for is the event red or yellow or purple. So that should kind of ring a bell in your head. Okay, it's or, so we must be adding probabilities. Now, when you're adding probabilities, you want to double check and see, okay, well, are these events mutually exclusive? Is it possible for a Skittle to be both red and yellow, or both yellow and purple? Well, no. So it's going to be just either red, or it's just going to be yellow, or just purple, or it's going to be another color, right? So those events are all mutually exclusive, which means we can just simply add the probabilities together. We don't have to worry about subtracting any overlap. Okay, well, what's the probability of it being red? Well, there are 4 red ones out of the 20. Probability of it being yellow, that looks like that's 3 out of 20. And it looks like we only have 1 purple, that's a 1 out of 20. All right, so we can go ahead and add those probabilities. We get 8 out of 20, which is equal to 2 over 5. You can leave your answer as 2 out of 5 as the probability. If you want to write it as a percent, that would be 40%. Okay, in example 5, we are going to use a random number generator and select an integer from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? When you see that word all 3 numbers, that should indicate to you that what's the probability that the first number is this, and the second number is this, and the third number is this. So in this case, what's the probability that the first number is less than or equal to 5, and the second one is less than or equal to 5, and the third one is less than or equal to 5? So the and should ring bells in your head that we are going to have to multiply those probabilities. So the probability that the first number is less than or equal to 5 times the probability that the second number is less than or equal to 5 times the probability that the third number is less than or equal to 5. Okay, now this works because these are 3 independent events. After you generate that first number, it doesn't affect how the computer selects the second number. It doesn't affect how the computer generates that third one. Okay, so these are all independent events. So what's the probability that the first number is less than or equal to 5? Well, from 1 to 20, 1, 2, 3, 4, and 5 would all be less than or equal to 5 out of what? Out of 20 numbers. So 5 out of 20. Second number is less than or equal to 5, same thing, 5 out of 20, 5 out of 20. And then you multiply those together, we get 125 over 8,000, and simplify that, that's equal to 1 over 64. So what's the probability that all three numbers are less than or equal to 5? 1 in 64 chance. Okay, now we're going to talk about binomial probability, now that we've talked a little bit about some basic concepts of probability. So in binomial probability, this is probability where there are four things. First, there are a fixed number of trials. Second, each trial is independent of the others, so they're each independent events. Third, there are only two possible outcomes, P and Q. And fourth, the probability of each outcome remains constant from trial to trial. Now, in general, how do you find the probability of what we call a binomial event? Okay, so in general, to find binomial probability, if you have two mutually exclusive events, P and Q, the probability of an event P occurring exactly R number of times is given by this formula here. Now notice at the front we have N choose R. What does that do? That's coming up with all the different ways that you could have P occurring. It could happen the first time, it could happen the second time, but it's still a different way of it occurring, and we need to account for all those different ways that we can have P occurring exactly R times. Okay, and then we have P, the probability of event P happening, raised to the R power. So if it happens R number of times, you multiply P that many times. And then Q is, because this is a binomial probability, it's either P happens or Q happens. So if P doesn't happen, then that must mean Q happens. Well, how many times does Q occur? Well, out of N number of times, if P occurs R times, that must mean Q occurs N minus R times. And that's how we get that exponent there. So just as a reminder of what everything represents, N is the total number of trials, R is the number of successes that are needed, P is the probability of success, and then Q is the probability of failure, which you can also find by doing 1 minus P, because P and Q are the only two possible outcomes. Okay, so let's take a look at example 6. It says a test consists of 10 multiple choice questions with 5 choices for each question. As an experiment, because you would never do this otherwise, you guess on each and every answer without even reading the questions. What is the probability of getting exactly 6 questions correct? Okay, so for each question, you have 5 choices, and only one of them is going to be correct. So that means for each multiple choice question, what's the probability that you have success, the probability that you get the question correct? That's going to be 0.2, right? 1 out of 5. Now, what's the probability of getting it wrong? Well, that's 4 out of 5, so that's going to be 0.8. Okay, so P is success, Q is failure. Now, how many times do we do this? Well, there are 10 multiple choice questions, so the number of quote-unquote trials is 10. And how many number of successes are needed here? Well, it says, what is the probability of getting exactly 6 questions right? So that would be 6. Right, number of successes needed, 6. All right, so now we can go ahead and plug it into the formula. So 10, choose 6. And then probability of success, or probability of being correct, is 0.2. Raised to the 6th power, because that's the number of successes that you need. And then times Q, the probability of getting it wrong, is 0.8 raised to the 4th power. Okay, so multiplying that out, we get 0.006, which is 0.6% chance of getting exactly 6 questions correct. Okay, let's look at the next example. At a certain intersection, the light for eastbound traffic is red for 15 seconds, yellow for 5 seconds, and green for 30 seconds. Find the probability that out of the next 8 eastbound cars that arrive randomly at the light, exactly 3 will be stopped by a red light. Okay, so let's define what is success and what is failure. So we're trying to find the success being stopped, right? Because we're trying to find exactly 3 will be stopped, right? So we'll say success is being stopped and failure is being not stopped. Okay, so for us to figure out so assuming that we're all obeying the laws of traffic here, okay, if you're stopped by a red light, so we need to figure out, okay, how many seconds are for each? It looks like 15 seconds for red, 5 for yellow, and 30 for green, and then it'll continue to cycle. So it looks like in total there are 50 seconds that are accounted for here. And of those 50 seconds, 15 of those 50 seconds are when the traffic light is red. So success is being stopped, so that would be 15 out of 50. Failure is not being stopped. So notice here, it's not when it's green, it's just when it's not being stopped. So that's everything else. So you do need to think about binomial probability as just one or the other. So either there's a red light or there isn't a red light. Okay, so you have to account for both the yellow and the green. So that's 35 seconds altogether. So 35 out of 50 will not be stopped. Okay, so now find the probability that out of the next 8 eastbound cars, so out of 8, so your number of trials is 8, exactly 3 will be stopped by a red light. So R is the number of successes that are needed, which is 3. All right, go ahead and plug that into the formula. So 8 choose 3 times 15 over 50 to the third, 35 over 50 to the fifth, and that comes out to be 0.254, which is equal to 25.4%. Okay, we have one last example to go over. So in this last example, Team A and Team B are playing in a league. They will play each other 5 times. If the probability that Team A wins a game is 1/3, what is the probability that Team A will win at least 3 of the 5 games? Now this example is slightly different from example 6 and 7 because in example 6 and 7, we had it occurring exactly 6 times in example 6. In example 7, it was exactly 3 will be stopped, but in this one it says at least 3 of the 5 games will be won. So notice that means that at least 3 means winning 3 games or 4 games or 5 games. And what we need to do here is we need to find each of those probabilities and add them together. Why do we add? Well, it's 3 or 4 or 5. So that indicates that or indicates that we are adding them together. So we'll independently find the probability of getting exactly 3 of the 5 games, 4 out of the 5 games, 5 out of the 5 games. Calculate each of those binomial probabilities, and then we'll add those probabilities together. So 5 choose 3, it's 1/3 of a chance of winning to the third, 2/3 of a chance of not winning to the second, and then we do the same thing with 4 and 5. So 5 choose 4 is 5 choose 4 times 1/3 to the fourth times 2/3 to the first. Then next we have 5 choose 5 times 1/3 to the fifth, 2/3 to the 0. Now we found all 3 of those probabilities, and we will just go ahead and add them together. Once you've added them together, this comes out to be 0.2099, which is about 21% chance. So the probability that Team A will win at least 3 of the 5 games is 21%.